So hello everybody. We are looking at switch linear systems today. So we look at stabilizability and stability of such systems in this video. So first of all, let's look at what a switch system is. So a system is a system where the derivative of the states is something that keeps varying with AI, right? So it doesn't remain constant. And if this AI varies with time, as I is equal to a sigma of t, a signal function, then we call it a continuous time system. And so we first look at stability under arbitrary switching. So what that means is that, take cases where all AIs are stable. Does that mean that the entire system is stable? So does the entire system approach zero? We can't guarantee that. So what guarantees that? So there are some special cases where, like if all AI AJ commute, then that is enough. But in general, we need something called a CQLF, common quadratic Lyapunov function. So what this says is that, there are individual Lyapunov functions for every AI. So if the same Lyapunov function holds for all such AIs, then we can assure that the entire system is stable. So we can algebraically write this into as linear matrix inequalities LMIs, such as PAI plus AI transpose P should be less than 0. If this happens, then we definitely have a CQLF, right? So this has been, there has been a lot of math done on this, and we get this stability equivalence theorem. So this states that there are three statements which are very equivalent, right? So if one is true, then the other two are true as well. So one statement is that there exists a CQLF. The second statement says that matrix pencils are Hurwitz. Third statement says that A1 A2 and A1 A2 inverse do not have any real eigenvalues. Also, this only holds for Hurwitz matrices A1 A2 in R2 cross 2, right? So what is a Hurwitz matrix? So Hurwitz matrix is when the eigenvalues are in the left half plane. So what does it mean when we say matrix pencils are Hurwitz? So this is a matrix pencil. So gamma alpha a1 a2 is alpha a1 plus 1 minus alpha a2. So this is a set of matrices. It is called Hurwitz when every matrix in this set is a Hurwitz matrix, right? So first, now we try to derive two results. The first one is something that ensures the existence. So we take AI as any general matrix, we find the lambda, that is the eigenvalues. Now we consider cases only where AI equal to DI, and now we simplify and try to make both gamma alpha A1 A2 and gamma alpha A1 A2 inverse Hurwitz. What we get is the condition where 2A1 A2 is greater than B1 C2 plus B2 C1, and at the same time greater than minus B1 C2 plus B2 C1, greater than equal to, I'm sorry, right? So we summarize it into these 3 points. When these 3 points hold, then the system has a CQLF for sure, and it is stable under arbitrary switching. We take a random example, that satisfies all three conditions. We see that a Lyapunov function of x squared plus y squared is good enough to act as a CQLF, and we see some trajectories as well. So you see that A1 and A2 have trajectories approaching 0 in slightly different ways, not exactly same. Now we also see the trajectories of the switch system. We see that there are non-differentiable points in the trajectories, but it still does manage to approach 0. So this is what is a stable switch system, right? Now the second result. So the second result, what we try to do instead of taking AI plus DI equal to, sorry, AI equal to DI, we consider DI equal to 0. Okay, so in this case, we by default require BICI to be less than 0, right? So if this happens, then A1 and A2 are Hurwitz. Now again, we try to make sure that gamma alpha A1 A2 and gamma alpha A1 A2 inverse are Hurwitz. But what happens is that we try all several cases possible, but we we understand that such a system is not possible at all. So if we have AIDI 0 and BICA is less than 0, then the system does not have a CQRF, but it does not prove that it is unstable. So that should be noted as well. Finally we also look at stabilizability. So stabilizability is when like we talk about systems where like AIs are unstable, so we find a switching signal that stabilizes the system as a whole, even though the subparts are unstable, right? So we do that by minimizing for this function over here, x transpose PAX, right? So if we minimize this and augment this, we get a switch signal. So this is the switch signal that will be able to minimize it. which will be able to stabilize it. And the switch system is only stabilizable if the matrix pencil gamma alpha contains a stable any stable matrix within it. So this is what is stabilizability. Thank you guys. Thank you so much for listening.